Hello and welcome to my presentation about the design and validation of a transfemoral prosthesis for use in powerlifting. The overall aim of this project was to design a transfemoral powerlifting prosthesis specifically capable of performing a barbell weighted back squat. This will improve the rehabilitative options for amputees along with improving the competitive para-powerlifting sport. Currently, para-powerlifting only involves the bench press, which is performed lying down, whereas able-bodied powerlifting also includes the squat and the deadlift, which are both standing motions. To achieve this overall aim, specific objectives were determined, to which the first one was to determine the biomechanical principles of the squat. The second is to design a novel knee joint mechanism capable of performing the biomechanical principles found. The third was to design a suitable actuation method, again, capable of producing the large torques necessary in a squatting motion. And then finally, to design a control system that supports the squatter during the exercise. So the first objective, to determine the biomechanical principles of the squat. Unfortunately, due to the way of the world when I was conducting this research and the restrictions that were in place, it was not possible to do a human movement trial. Therefore, literature was needed to try and find the input joint angles that a human movement trial would have given. Fortunately, the paper from 2012 by Swinton et al. Was used. The graph in that is shown on the left-hand side. And as you can see, this was not designed to be read off of for input angles. Therefore, it was recreated in PowerPoint by overlaying curves, meaning that there could be 101 read-offs representing 0 to 100% of the lifting range. This was also recreated for the vertical ground reaction force, as again that was necessary in the kinematic analysis and kinetic analysis. A moving average smoothing function was used on the input angles because the way that the angles were read off led to a lot of granulation. This was particularly prevalent when there wasn't much change in the joint angle, as this was rounded to the nearest degree, as that was all that was feasible to read off. There'd be no change in joint angle, which isn't particularly accurate for if you think about what a squatting motion is. Therefore, when calculating the reaction forces and particularly the moments about the joints, there was a lot of noise in the system and it wasn't particularly usable. Therefore, using the smoothing function gave a much more realistic curve to the input angles and gave the joint moments that you can see in figure 3 there. Looking at figure 3 on the left-hand side were the joint moments found by the kinetic analysis of this project, and on the right-hand side it's compared to a paper from 2008 by Robertson, Wilson and St. Pierre. The results were deemed accurate or usable as the results comparably were of the same sort of magnitude. Along with that, the shapes of the curves were very similar. This is particularly promising, seeing as this is two different data sets with different lifters, and all lifters have slightly different and unique ways of lifting. In addition to that, the recordings may have been started and stopped at different times with different definitions of when the start and the end of the squat is. So overall, these results were deemed accurate enough to continue with using for the rest of the project. Moving on to the second objective, which was the design of the novel knee joint, the knee joint mechanism. For this, a 6-bar linkage system was designed, as the 6-bar linkage allows for not only the rotation about the knee joint, but also the internal translation. This is important because any errors at the knee joint will transfer into the hip and thus the pelvis, causing twisting and potential lower back issues for the user. To design the 6-bar linkage, the paper by Jin et al. From 2003 was modified in Linkage 3.0 software to elicit the correct range of movement required for the squat motion. The first iteration of the linkage system can be seen on the left-hand side, comparing to what is expected for the actual lifter, calculated from the Swinton et al. Input angles. And as you can see, there is some error at the knee, but there's really quite significant error at the hip joint. This would cause too much twisting and likely injure the user or just render the system unusable. Therefore, it was decided that an improvement process had to be implemented. This involved varying the lengths of the L11 and L13 linkages shown on the previous slide, as it was not possible in the time permitted to do an overall linkage optimization. However, with just this crude improvement process, the errors reduced by an average of over 50%, which proves the concept that if more time was given and a more rigorous method was used, these errors really could be significantly reduced. Moving on to the fourth objective, which was to design the suitable actuation method. First step of this was deciding which linkage would be actuated, and this was chosen to be the joint between the first and fourth linkage shown in figure 6. This was chosen as L1 represents the top of the shank section and L4 is the longest length going off of that. So being the top of the shank section is a good place to attach the motor, and then having the longest linkage off of that will reduce the amount of torque required at that joint. Once defined this suitable location, it was necessary to understand what the torque is at this point, because overall knee joint torque doesn't represent the internal joint torques of the 6-bar linkage, and for this the rigid dynamic solver in ANSYS was used, using the resultant forces from the kinetic calculations kinetic calculations, and the temporal data from Swinton et al. And this found that the motor requirement was 500 Newton meters. This is a lot of torque from what should be a small motor. Therefore, a compact design of the ILM 85x26 motor kit was chosen, which supplies 2.9 Newton meters of torque. Therefore, a sun and radial gear assembly was designed, which had a step up of 1 to 196, and you can see the assembly there in figure 7. This is a representation of what the knee joint could be. As you can see, the 6-bar linkage is mirrored on either side to help with any rotational force or lateral stability. You can see the motor is central with gearing systems either side, and you can see how it would affect to what is called there as the base bracket, which is a representation of where the shank would be. Finally, the fourth objective was to design the control system that supports the squatter during the exercise. The key point about the control system was that it couldn't overpower the healthy leg. The prosthesis must support and not overpower, because that could be dangerous for the user, lifting something that they're not physically capable of lifting. To get around this, it was decided that the prosthesis would mimic the healthy leg, and with this, the IMUs would be used on the shank and thigh to have a knee joint input angle for the control system. The knee joint angle can be assumed to be a quadratic input, therefore steady state error had to be 0 for anything lower than a quadratic order. You can see there it had a very fast settling time and rise time, meaning that the mimicry was very quick. Finally, I'd like to conclude by just talking about the future work of the project. There are immediate next steps, which I've already mentioned, which it would be to, for example, the 6-bar linkage optimization. If the human movement experiment could go ahead, that would help, along with looking at different height people and different sexes. Look at the effect of disturbance on the control system with leg shake or soft tissue artifacts. The ankle joint would need designing. That can be done in a very similar way to the way the knee joint has been done, and to find a socket attachment method that would be suitable for such high strains. Now, future iterations of the design could include capabilities for more lifts, such as the deadlift, to simplify the design to reduce the cost so that it's more accessible to people, and then finally to incorporate machine learning into the control system to make the the user more at one with the device, so it can learn their particular way of squatting. So that is it for this presentation. I hope they find that interesting, and thank you very much for coming along and listening.